In this particular video, since we have a planet orbiting some distant star, and the planet has a radius of 3.24 times 10 to the 6 meters, and it says the escape speed for an object launched at the planet's surface here is 7.65 times 10 to the third meters per second, and it wants us to find the acceleration due to gravity, so little g. Alright, so let's go ahead and crack this out. I'm going to go ahead and draw a sphere here to represent whatever planet this is. And then I'm just going to label stuff that's given to me. So here is the radius of this particular planet. That is 3.24 times 10 to the 6 meters given in the wording. And then here is some object from the surface of the planet. It's going to have an escape speed of 7.65 times 10 to the third meters per second. Okay, so keep in mind that it wants to find acceleration due to gravity. So in order to do so, there's the escape speed given in the problem. I do want to point out that when you're at the surface of the planet, there is some sort of gravitational potential well that's holding on to you. That is a negative quantity. So essentially, this is how much you owe in order for you to get off the planet. You have to put in enough kinetic energy. So this V escape here dictates how much kinetic energy you need to put in order for you to be unbound by this particular planet. All right, so to do so, I'm going to make a true statement that the kinetic energy, the minimum kinetic energy that you need to put in must equal to the gravitational potential here that's holding on to you due to the planet, which is a negative value, okay? All right, so other than that, I'm just going to set Ke is equal to U. You notice on the right side, there is no negative sign because here we're just dealing with energy anyway. So the energy you put in must equal to the energy that you owe. Other than that, the mass cancels out, or the mass of whatever object that's being launched here is going to cancel out. So I want to cancel out on both sides. Here on the left side, it simply reduces down to V escape squared divided by 2. Again, multiplying by half is the same thing as dividing by 2. So I'm just going to go ahead and put the 2 in the bottom there just so that it looks a little cleaner. All right, on the right side, you notice I just carried down everything that I haven't canceled out, which is the universal constant, mass of this particular planet, and then the radius of the planet here. So I do want to find g, but you notice here in this particular statement, I don't have acceleration due to gravity, little g, anywhere. So at this point, you just have to get a little clever in terms of how to manipulate this function so that you get a little g in there. All right, so I'm actually going to go ahead and multiply the right side by r on the top and r on the bottom. Okay, so there's a reason for it. That's because when you do this, you can get the right side to have big G, or the universal constant, times m divided by r squared. Multiplying top and bottom by r over r is just like multiplying by 1. But doing so allows us to introduce another r in the denominator, which will get it to multiply, which will make into r squared. Now, why would I want to do that? Okay, so here's on the right side. The left side I haven't done anything, so just in case you're not keeping up. So here on the right side, I rewrote it where I put gm over r squared. So I multiply r on the bottom, r times r is r squared, and I kept the r in the numerator separately. Now I did this because I know that little g, acceleration due to gravity, so this term that I'm highlighting is gm over r squared. Okay, so there was a reason why I multiplied the right side by both r on top and r on the bottom. That's because I recognize that if I do that, I can get this term gm to be over r squared. Okay, well, gm over r squared is just acceleration due to gravity at the surface. So therefore, wherever gm over r squared is, I can just replace that with g. So here, I'm just going to go ahead and replace this whole highlighter with g. But you know that there's still this little capital R on the right side. So to get g by itself, I will go ahead and divide both sides by r, or I'm just going to move this r on the right to the bottom left denominator. So it becomes v escape squared divided by 2r. So I have an expression now for g. And I think this might be the hard part for folks to recognize. How do you manipulate this energy function to introduce little g in there? But you have to know what's highlighted in yellow, okay? So hopefully by now, if you're taking physics, you've been exposed to this function when you've dealt with universal gravitational attraction, okay? All right, other than that, everything else is given to you. V escape is given to you in the problem. Don't forget to square that. And then here, 2 is just part of the function that I manipulated. And then the radius of this particular planet is given as 3.24 times 10 to the 6 meters. And if you plug it all in the calculator properly, you should get a value of about 9.03 meters per second square. And here you can just say the acceleration is pointing towards the surface of the Earth, towards the center of the Earth, okay? But this is just the magnitude. The problem didn't specify, so I'm just going to say 9.03 meters per second square towards the center of the Earth. All right. Other than that, this is a slightly different way to see it. Same thing, it'll give you the same result, but again, just slightly different view to see it. So I'm just going to start with this v escape squared divided by 2 equals g big M, the mass of the planet, divided by the radius of the planet. That's because I derived it here. So watch where I'm circling back and forth with my cursor, all right? So I start with energy, I'm going to end there. But what I do recognize is that capital G and the mass of the planet is just a constant, right? So what I can do is I can go ahead and solve for big G and M all together. So because both of these are just a constant, so they just represent another constant. So now why do I want to do this? If you recognize this right here on the bottom where G, acceleration due to gravity, is big G times M divided by R squared, you can use that as well. Okay, so it all comes down to how familiar you are with these physics functions. Well, here I can just apply this little g, acceleration due to gravity is capital G times M divided by R squared. But you notice here in the statement, I also have a G and an M, which are the same two constants as the previous statement. So I'm going to go ahead and solve for G and M by simply multiplying both sides by R squared. So here I have a statement that says G times M is also equal to little g times R squared. Well, I have two expressions that represents both capital G and M, right? So both of these boxes that I'm highlighting here represents capital G and M. Well, because they represent the same quantity, I can set the two functions equal to each other. So I can say v squared times r divided by 2 is equal to lowercase g, acceleration due to gravity, times r squared. Well, here's an r on the left side. I'm going to cancel out with the r squared on the right side, just one of the r squared. Okay, so I'm just going to cancel the square term out. So as you can see here, it really leaves us down with the same statement. To get g by itself, you would divide both sides by r, as I did previously on the left side. So once you do that, you notice here you have the same statement. So to find lowercase g, it would just be v escape divided by 2r. And I'm just going to stop here because I've already done it on the left side. This is just a different ways for you to see how to kind of manipulate these functions to get what you want. Okay? All right, I hope that helps. Stay nerdy, don't be white.